Hello and welcome to this, my video on inverse matrices and solving simultaneous equations using matrices, part of the General Maths Year 11 course. My name's Darren, thanks very much for joining me. Hopefully you're going to find this content useful. Before I get into it though, can you do me a massive favour and obviously subscribe to my YouTube channel? I say obviously because if you watch my previous videos, I seem to ask this at the start of every single one. Why? Because I'm sitting in a room talking to myself and going ever so slowly mental. But if you click that subscribe button, it just lets me know that people are actually watching. It's huge to me, and just a little click from you. I'm also on, TikTok and all those other things as well. Now this video is building on my previous videos. What are we going to do in this one? Be able to find the inverse of a matrix and be able to solve simultaneous equations using matrices. Ooh, I don't know about you, but I tended to shudder every time I think about simultaneous equations from year 10. Standing there trying to teach people to do it by elimination and substitution and maybe even graphically if you were lucky. But don't worry about it. I'm going to show you a lovely, beautiful way to do it using matrices. Now at the end of the last video, I actually said to you, guys, really sorry, you can add matrices, you can subtract them, you can multiply by a scalar, you can even multiply matrices together by hand and using a CAS, so long as the orders allow you to do it or they are defined, but we can't divide matrices. But that's silly. Surely there's got to be a way to divide matrices, and that actually is because you have to use a trick. And at the last video, I talked about the identity matrix. So let's get a little bit into the theory, and then I'm going to show you how we can do some pretty funky maths to help us divide matrices. The identity matrix. Now, if you remember, the identity matrix is a square matrix that basically has ones on the leading diagonal, zeros everywhere else. So for example, he says, writing in highlighter again, that is an example of an identity matrix. It's a 1 by 1, and they have always got to be square. Okay, so identity matrices are always square. By that I mean they have the same rows and the same number of columns. Right, so this has 2 rows, it has 2 columns, it is a square matrix. Let's do one more. Right, 3 by 3 has 1s on my leading diagonals and 0s everywhere else. Right. And what did we decide? Well, when we had at the end of the last video that we knew that when we multiply by the identity matrix, then ultimately you were multiplying by 1. Okay, but there's something also pretty funky. And it says here that if I take a matrix and multiply it by a to the power of minus 1, the same matrix to the power of minus 1, I will always get the identity matrix. And also, if I do a to the minus 1 times a, I'm always going to get the identity matrix. Now again, don't worry if you don't fully understand what a to the minus 1 is. I'm going to come up to that later. But what I know is that if I take a matrix and multiply it by its inverse, and that's the format, that's the notation for the inverse, or I take its inverse and multiply by the original matrix, I will always get the identity matrix. Why? Don't care. University maths, really not interested, not going to lose any sleep over it. Trust me, let's just accept it and move on because it's general maths. That's what we want to do, yeah? Yeah, marvellous. All right, so let's find out what this a to the minus 1 is. Ooh, now that looks pretty horrendous, doesn't it? Yes, but it actually is relatively simple when you understand. So if we say that matrix A has the general form where we have A, B, C, D. So let's have these 4 numbers where we are giving them letters A, B, C, and D. To find the inverse, and again, this is just a pattern, a rule, something for you to learn. The first thing we do is we swap the values of A and D. They literally just swap places. Next thing we do is we look at the values of B and C and we times them by minus 1, right? So we actually negate them, we times them by minus 1. Now the way we do that here is we say it becomes minus B and minus C. But what I mean is if that number was minus 3, it'd become a 3. If it was 7, it would become minus 7. So we negate it. So that's the first part. So that's what this section here is. We take it, we swap the corners, those two, and they become just the minus or the inverse of what they were before. Now, where's the rest of it come from? Times by. It's always 1 on. And what we then do is we actually multiply opposite corners together and subtract them. So we do A times D, and we subtract the multiplication of the opposite corners, B times C. Ka-ching, that there is my inverse of matrix A. Now again, I'm going to show examples of what that means in a moment because we're doing it with the letters. But it is important to know that this bottom bit here is, as I've said here, it's called the determinant. That becomes really, really important because if you know anything about fractions, there's one number that can't be. There's one number we can never have on the bottom of a fraction, or it gives us infinity and beyond, or undeterminate, or whatever else. So I've shown you here how we can go from a matrix to its inverse. Let's have a go with actual number answers or number questions. So we are now going to find a to the minus 1. So it becomes 1 on. I'm going to do it in a different order this time just so that we can. So if you remember, we do the opposite corners times together. So 8 times 2, so let's write it out longhand. 8 times 2 minus those two corners together, 3 times 4. And then we draw our square brackets. And what have we got? If you remember, we swap the corners. So those two corners swap places. So that becomes 2 and that becomes an 8. And what do we do to the other numbers? Well, if it's positive, we make it negative. If it's negative, we make it positive. So that's positive 4. I'm going to make it negative 4. And there's positive 3 there. So that becomes negative 3. Now, obviously, we don't leave it like this because we'd actually have to work out what that section there is. So that becomes 1 on, well, 8 times 2 is 16. I'm going to do a little subcalculation up here. 3 times 4 is 12. Take them away becomes 4. So it becomes 1/4. So let's get rid of that massive sign there. Of 2 minus 4 minus 3 and 8. Now I've run out of screen real estate. But do you notice that number is outside the brackets? Yeah? We could in a previous video have written it like this, 1/4. It might have been a small number outside. More than likely, it would be a whole number. But realistically, this is just a scalar multiplier. What I should really do now is do 1/4 of 2, 1/4 of minus 4, 1/4 of minus 3, and 1/4 of 8. Why? Because actually that's what your calculator is going to do. But we don't need to. We can happily leave it like that. And that there is an example of an inverse. Now again, I'm going to show you how to do that on a calculator, and in ClassPad, guys, it's pretty much the same, all right? So what I'm going to do here is I'm going to use the calculator notation. So let's do that. So I've got 8, 4, 3, and 2. And again, I can raise that to the power of minus 1 to find my inverse. So I'm going to raise that to the power of negative 1, and I'm going to hit enter. And you're going to notice there that, hold on a moment, that doesn't look anything like what I had before. Yeah? Where on earth has that 0.5 come from? Well, oh dear me, sorry guys, let's just try that one again. 1/4 of 2, or 2 divided by 4, is actually 0.5. The minus 1, this minus 1 here, is coming from 1/4 of negative 4. Now your calculator doesn't know how to put the fractions outside, so it'll always give you decimal values or fractional values depending on what your calculator is, but it doesn't matter. It doesn't matter because we're just going to use it later on in the next step. Now the determinant of a matrix, this bottom bit here, is really, really important, all right? Because if you go back to what I said a moment ago, what number can't that be? It can't be 0. We cannot have 0 on the bottom of a fraction. So if this value is 0, we cannot have an inverse, and that becomes really important later on. If this value here is not 0, then we can have an inverse. So again, that's really important. This number here is 0, no inverse. If it isn't 0, it's an inverse. We can have an inverse. And the bottom bit, not the whole fraction, just the bottom bit, is called the determinant. So the determinant of a matrix is equal to AD minus BC, where that matrix is defined as having A, B, C, and D. Let's find the determinant of each of the following matrices. Now in this situation here, I'm not finding the inverse, I'm just finding the determinant. So that's nice and easy. So all I'm going to do is opposite corners multiplied and then subtracted from each other. So we write determinant of A, you got to write det, is equal to 5 times 6 minus 3 times 2. Well, 5 times 6 is 30, 3 times 2 is 6, So in which case the determinant there is going to be 24. And believe it or not, I don't care about the number. I just want to know whether it's 0 or not. So because that isn't 0, we know that that there will have an inverse. Let's have a look at the next one. So the determinant of b gives me, right? So minus 3 times minus 2. So it's minus 3 times minus 2. And we're going to subtract from that 2 times 7. I don't know why I've written those in brackets. 2 times 7. So minus 3 times minus 2 is 6. 2 times 7 is 14. 6 minus 14 is going to give me negative 8. Again, I don't care about the fact whether it's positive or negative or whatever else. Because that isn't a 0, that will also have an inverse. Now, go back to your year 10 stuff, simultaneous equations. If you did simultaneous equations, basically, simultaneous equations are just ways of writing straight lines. They are two straight line graphs. And what we are trying to do when we're looking at straight line graphs is trying to work out whether they cross or not. And if they do cross, where they cross. So for example, if I have two straight lines, they could be like that, yes? And what we notice is that there has one point that they cross. It has a unique solution. Happy with that. What other ways are there for graphs two graphs to be on? Well, I could have them that they're absolutely parallel. And if they're parallel, they're never going to meet. And if they're never going to meet, they're never going to have a solution. And the other way of doing it is, in fact, the graphs could be exactly the same. The equations could be exactly the same. They could sit right on top of each other. And in which case, that would have lots of solutions because every single point on every single graph is touching another point. So in this situation, we would say that that has one solution. This one here has 0 solutions. And this one here would have infinite solutions. Infinitely many because there would be so many. All right. Now, the great thing is we can use matrices to help us solve simultaneous equations. And when we're solving simultaneous equations, we're really trying to find out where two lines cross. That is it. And the determinant helps me do that. Because when it is a non-zero number, when my determinant is non-zero, there will always be one solution. All right, that will help us find the solution. If my determinant is 0, actually it stands for two situations. Either the two lines are parallel or the two lines are exactly the same. And trying to work out which of those is way beyond the scope of this course. That's methods and specialist maths, okay? But this is useful background information. Well, I say it's useful. I think it's useful. Rightio, so let's solve some simultaneous equations. First things first, we've got to learn how to put these into matrix form. So there are two simultaneous equations. They are just straight lines. If I was to draw those on a graphing situation, there would be two straight lines. Do they cross? That's the thing we're going to try and work out. Now, when we want to write this in matrix form, the first thing we do is we look at all the numbers in front of the x's and the y's, right? And I write those in a matrix. So the first thing I do is I'm going to write a square matrix, and I've got 1, 2, 3, 4 numbers. So I'm going to write 8, 2, 5, and minus 3. The reason it's minus 3 is because there's a minus 3 in front of the y. Now, be very careful in exams because sometimes they can switch the x and the y to try and trip you up. Because again, we're asking you to understand the maths, not regurgitate it. The next thing I do is I do a 2 by 1 matrix. And the reason I do that is because I now need to take account of these letters x and y. So I write x and y there. Now, if you're sitting there saying, why do I do this? Don't worry about it. I'll try and explain in just a moment. Just showing you how you do it. Then you do an equal sign. And then you put these last two numbers here in its own 2 by 1 matrix. So that becomes 46 and 19. So believe it or not, that is like linear form, and that there is matrix form. Now let's just check. Can I go from here back to here? Well, yes, you know how to multiply matrices, don't you? So you would do this row here times that column there. So 8 times x would give me 8x. 2 times y would give me 2y. And that would be equal to, well, in this situation, it would be equal to my answer there of 46. And if we do the same thing here, that row times that column gives me 5 times x minus 3 times y, I should put a plus in there, is equal to 19. And lo and behold, I have now gone from here back to here, and they just so happen to match. So being able to write equations in matrix form becomes really, really helpful to helping us solve simultaneous equations. Now, right, express the following simultaneous equations as matrices. All right, so let's do another example. I thought I was going on to the fun stuff, but let's do another example. Now, are my x's and y's in the same order? X followed by y, x followed by y, yes. So there's no trick to this question. So I just draw some square brackets. Right, 6 is in front of the x, I'm going to write 6 there. What's in front of the y? It is minus 1. Then I got minus 2 and positive 5. What's my next bracket got to have? Again, you just follow the rule, becomes xy. And the next one is the numbers at the end, which becomes 15 and minus 19. And believe it or not, that is in every exam I've ever seen, pretty much SACs, because this is going to be in some sort of a SAC, I can pretty much guarantee you. So it's important to know how to do this. Now we get to the matrix algebra. This is the funky stuff. This is where the identity matrix comes in. Now I'm just going to show you the long way of doing it and then say, hold on guys, there's a shortcut. Here's how to do it on your calculator. Just remember how to do this. Right, the first thing I'm going to do is I'm going to write these equations here in matrix form. To solve simultaneous equations, I've got to write them in matrix form. So we have 5, 2, 7, 3. xy equals 21, 29. Now, for some reason in matrices, we would generally call this capital A, we would generally call that capital X, and we generally call that C. So we know that A times X equals C. We want to get, when we solve this, we want to get these on our own, which means I've got to get rid of this. And what we would normally do is, oh, well, we can just divide these, don't we? No, because you can't divide matrices. So here we go. This is where the funky stuff comes. I'm just going to show it to you. You don't necessarily have to remember this or even know how to do it. It's just useful so you can see why it works. So A times X is equal to C. I've just written that out again. What I'm going to do to both sides of this is I'm going to pre-multiply by the inverse of A. So I'm going to pre-multiply that. So I'm just going to write A to the minus 1 times A times X. Now obviously in maths what we do to one side we have to do to the other, keep it balanced. So I'm going to pre-multiply A to the minus 1 times C. All I've done is there's my A times X, there's my A times X, there's my equals, and C. I've just pre-multiplied A to the inverse of A. Now the reason I've done that is, if you have remembered the stuff from the previous video, when we take a matrix and multiply it by its inverse, we get the identity matrix. Oh, hold on a moment. So there we go. So I now know that that can be replaced with the identity matrix times X is equal A to the minus 1 times C. But hold on a moment. We also found in a previous video that when we do the identity matrix times anything, that's the same as multiplying by 1. So the identity matrix times X is basically just X. So we again can say that X becomes equal to A to the minus 1 times C. Oh, hold on a moment, we've now got X on its own. So all this has shown is that to get X on its own, I just find the inverse of this and pre-multiply it by C. So in that situation, what I can now do is say that my value of xy is equal to, so we write out matrix A, 5, 2, 7, 3. I find the inverse of it, which means just raise it to the power of minus 1, and times that by C, which was 21, 29. So, can't do that in my head? Nah. So let's fire up my calculator. No, I've covered my screen for the moment, but fingers crossed we should be able to do this. So let's do my 2 by 2 matrix. What do we have? 5, 2, 7, and 3, he says. I don't know what's going on there. Let's actually put the numbers in. 5, 2, 7, and 3. Raise that to the power of minus 1. Don't forget the times sign or your calculator gets really upset with you. And what do we want here? We've got a 2 by 1 there of 21 and 29. Hit enter, and there we go. We get a solution of 5 minus 2. Now what that means, turning off my calculator, is therefore my x value is equal to 5, my y value is equal to -2. So to make this equation work, I would substitute x as 5 and y as -2, and I would get each of those values there. Alternatively, if I was thinking about these in terms of simultaneous equations, and I had two equations which crossed, it would tell me that this crossing point here would have the coordinate 5, -2. And my diagram there is shocking because you'll be like, yeah, but hold on a moment, -2 should be below. It's just a sketch, just giving you the idea. So this stuff, really, really important. Can we use the CAS? Absolutely, we can use the CAS, and I've just shown you how to use the CAS. So again, in this situation, if I was just given that question and I wanted to go at it with out all the matrix algebra, I would write this out first as 5, 2, 7, 3. xy equals 21, 29. And then I would go straight to the next line and go that xy is equal to 5, 2, 7, 3. Remember, because I've moved it to the other side, I've got to do its inverse, times by 21, 29, put it into my CAS, and out would come my answer. Now, practice is really going to make perfect here, so my general advice to you is, or my huge advice to you here is practice, 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 and practice again. Use your calculator, do it by hand. I have no idea what's going to come up in tests for you guys. Sometimes you'll be able to use your calculator. I know that we sometimes ask our kids to do it by hand because it's important to know how to do these things. But I'm done. That's the end of this video. There's more to come. Hopefully I'll see you in that. If not, take care. Please stay safe.